Welcome to this massive open online course on advanced analytical technique. And in the previous slide, we have introduced the concept of gas chromatography. And we have also covered the basic principle of gas chromatography. We have also seen the various important components which constitutes a gas chromatograph. And in addition, we have also studied the carrier gas, the concept of carrier gas, the importance of carrier gas, and then we have also discussed about the flow meter, the importance of flow meter in gas chromatograph. Then we have also discussed that how actually the flow regulators has an impact. We have also studied the sample injection port, and we have discussed three different type of commonly used sample injection port, namely the split injection port, splitless injection port, and the third one is the on column injection or on cold injection, it may also be sometimes called. Now we are moving towards the heart of the chromatograph. That is, now we are actually moving towards the chromatographic column. Now the chromatographic column is the main part where actually different components of the volatile sample actually gets separated. So basically speaking, this chromatographic column actually is broadly classified into two categories, namely the packed column and the open tubular column. This open tubular column is sometimes also referred as capillary column. So as the name suggests, that packed column where we have the stationary phase actually packed, and the capillary column, of course it's also a sort of column, and we are going to see the fate of the stationary phase in this type of column. So again, before going into the detail of the packed column and the capillary column, what are the criteria on the basis of which we decides the utility of a particular column with regard to separation. So the important criteria are efficiency. Okay, number one, the foremost one, sample size. For example, if we are using a large sample, then of course we have to go for the packed column. But if our sample is very superfine, then we can go for the capillary as well as the packed column. Similarly, the resolution in the capillary column is the best one, is the highest resolution. Similarly, with regard to analysis time is least in case of the capillary column or the open tubular column. So we are going to study these factors, and before going into the detail of these factors, let us first understand the basic difference between a packed column and an open tubular column, or simply capillary column. And once again, the important message is that this is the main part of any gas chromatograph. Okay, let's begin our journey. So we have two different type of columns. One is the packed column and another is the open tubular column. So each column has certain advantages and each column has certain disadvantages. So packed column with regard to the gas chromatograph is actually of two types. For example, let us get a cross-sectional view of a packed column. For example, if we have, this is the cross-sectional view. Let us suppose that this packed column is of the GLC or simply the GC. Then in GC, that is gas chromatography, or simply sometimes it is called as gas liquid chromatography. Now here, in this, that the liquid actually, your stationary phase is a liquid which is immobilized on the solid surface. So here your liquid is actually immobilized on it, covering the stationary phase particles like this. Similarly, what happens is this: for example, if you have GSC, that is the gas solid chromatography, then here if you get a cross-sectional view, then you will get like this. In the cross-sectional view you will get like this. Here the stationary particles are not actually covered, but here the adsorption occurs. Here the adsorption occurs. So generally, for the packed column, the stationary phase, the solid, this solid is generally the diatomaceous earth. What is actually needed at this point of time is that in when we talk about this packed column, the important thing is that the length is small here. The length is only 1 to 5 meter, and the diameter is too big. Okay, this actually big diameter gives you an opportunity to partition or to separate your large in terms of quantity, large quantity of your sample, because the diameter is large. So you can, in a single go, you can take large amount of sample, but at the same time the length is small. It is 1 to 5 meter, and this small length actually gives you compromised efficiency, because as the length is small, the height equivalent to theoretical plates, or you can say the number of theoretical plates are less. So if the number of theoretical plates are less, then the efficiency, or you can say the resolution, is not good. So of course you can take high quantity of sample. It is easy to handle, simple, robust, and it is cost effective also. But the disadvantage is this, that it is less efficient, because now band broadening will occur, and the greater pressure drop is also there, and again it will take more time to run your sample. So these are actually the limitations with regard to packed column. But again, there are certain, for example, if for a newcomer you can use a packed column because it is easy to handle. So there are certain advantages and there are certain disadvantages. Let us see what the open tubular column has give to us. So open tubular column, or simply capillary column, these are the wonderful columns, and these are, you can say, upgraded columns. Initially, with the advent of the gas chromatograph, packed columns are the oldest columns. These are the traditional columns. And these are the modern columns, that is the capillary columns, or the simply you can say open tubular columns. Now you can see the length is too high, that is, it can go up to 100 meter. This is huge, but at the same time the diameter is less. That means that you can, at one go, you cannot analyze too much quantity of your sample. But at the same time, here there are certain advantages. Now broadly speaking, these open tubular columns or the capillary columns may broadly be classified into two categories, that is the wall coated open tubular columns and the support coated open tubular columns. And again, these two subcategories have certain advantages. For example, if we want to discuss this wall coated open tubular column, then if you want to draw a cross sectional view, then this is like this. So most of the time when we talk about the open tubular column, we should remember that these columns must be made from high tensile substances. Generally, these open tubular columns are made up of stainless steel or fused silica, that is high quality glass. So because they have to bear tremendous amount of pressure, and at the same time they have to undergo the heating up to 450 degrees centigrade in certain cases. So the substance from which they are made must have high tensile strength. They must have very good, you can say, thermal stability. So if you want to draw a cross sectional view of WCOT, that is the wall coated open tubular column, then what you see that your wall actually, it consists of, for example, if we are talking about a silica, then you have a silica, this wall is have silica, and the liquid is actually, which is mobilized, is is coated in a thin film. And this may be sometimes it is 1 to 5 micrometer thick, this coating. And if it is a silica, for example, if it is a silica, then you have to add certain protective coating on the top layer of it. Sometimes we use polyimide coatings, so that your column can be made resistant to scratches and various other you can say physical damages. So now you can see that this is actually your silica, and you have coated it from a thin stationary film that must be stable. Similarly, if you have a support coated open tubular column, then again it is like this. This is the column. It is made up of, for example, stainless steel, and what you do, you just adsorb a matrix, a supporting material in it, inside it. You take certain material and you coat it, and that coating actually, and on that coating you actually then immobilize your liquid or your stationary phase. And now here the column is ready for the separation. Now each of these WCOT and SCOT has certain advantages and disadvantages. Nowadays a new type of tubular column has also fascinated, that is called as the fused silica open tubular column, that is called FS, that is fused silica open tubular column. Now here the silica, which is actually a very high quality glass, is taken for making columns, and here these columns are highly efficient columns and they give you very good resolution. And the beauty of this is that because these are actually hollow in nature, so they give very less resistance to the flow of the carrier gas. So that is actually the beauty of using these capillary columns. And because there is zero resistance or very less resistance, so the pressure drop is not too much as compared to the traditional columns where the pressure drop was very high. So these columns are very good in terms of the running of sample time and in terms of the resolution, or you can say that they are very efficient in separating different components on the basis of the difference in their partition coefficient with the stationary phase. So again they are highly efficient, they give very high good resolution, that is your peaks, they give you well separated peaks, and low carrier consumption, because now your carrier gas will go without any obstruction. So the limitation is, because of the small size, you can only run very small quantity of sample. And again, if your column is made up of glass, then you have to take too much care of it, because these are fragile systems now. Okay, so now the temperature control. It is very important aspect. That is, in most of the time, for example, temperature itself so important for elution. For example, let us suppose that your mixture, your volatile mixture, has a component which has a difference of around 50 degree. Component A, for let us suppose a two component system, it has a boiling point of say 80 degree and it has a boiling point of, let us suppose, boiling point of 140 degree centigrade. Now simply what you have to do, you have to run your sample, this is actually mixture, when you mix it with your carrier gas, for example, let us suppose it may be helium, then it is going to elute first. That initially you will get a peak of A, and of course the area under the peak gives you the quantity of A. Then instead of waiting for too long, what you do, you just increase the temperature of your column temperature. The moment you increase the temperature, so instead of coming at a large, you can say, amount of time, the moment you increase the temperature, it will elute very fast. So what you do, you use temperature as your controlling switch, and this can only be done if your components have a large difference in their boiling point. So it is very good for where you have wide boiling point difference. Now if you have, for example, if your components are like this, if you have a 3-component system A, B, C, and it is coming at, it has a 60 degree, it has a 70 degree, and it has a, suppose it is 80 degree, then you cannot do temperature programming here. Then you can use the constant temperature, and it is actually the isothermal. You have to keep maintaining, you have to maintain the temperature. So on the basis of the nature of your volatility of the different components, you have to choose whether you are going to use a temperature programming or you have to simply run it in an isothermal fashion. So depending upon the nature or you can say the volatility or the boiling point of the different components, you can use temperature as a controlling switch. So again, what temperature has done? Temperature has actually increased your separation speed, and of course it has improved the resolution. The resolution improvement means that is now you have very good peaks coming after a certain times. That is, there is no actually overlapping of the peaks. So here the important factor is that your temperature actually has decreased the retention time. So the moment you increase the temperature, the retention time, that is TR, decreases the moment you increase the temperature. So this is the key point, and this is the point by which you can actually program your chromatogram, or you can say your GC. So stationary phase. Now this is one of the very important aspect, that stationary phase or the liquid phase, actually it determines the partitioning. Now for example, the most ideal characteristic is, first let us take the thermal stability. By thermal stability means that whatever the stationary phase, for example here in case of GC it is the liquid, whatever the liquid you are using, it must have around 100 degree greater boiling point as compared to the temperature at which you are running your GC. The temperature of stationary phase must be 100 degree above than the working temperature. Okay. Otherwise, what happens is, otherwise there may be chances that your stationary phase becomes unstable, and it will also start eluting with the sample. That is also called as the column bleed, which we are going to study. So for thermal stability, for maintaining thermal stability, your stationary phase must have 100 degree centigrade greater boiling point than any of the components of the vaporized sample. That is called, that is you have to maintain in terms of thermal stability. Similarly, low volatility and chemical inertness. Now low volatility and chemical inertness is that, again the thermal stability is also there, and you have to keep that K, the value of partition, that is the, you can say the retention factor K, that value of K must lie between 1 to 10, so that you can have an effective, or you can say you have good chemical inertness of your liquid phase. Similarly, for your alpha should be greater than 1. Because what happens is, that is, whenever your substance is partitioning, again the distribution constant comes into play, that is called as Cs upon Cm. Or simply you can say that if you are having alpha, then it is Kb upon Ka. That is how it is partitioning, that is, it is interacting with the stationary phase. Your component is interacting with the stationary phase, and if your K value is greater, too much greater, then it implies that the interaction is higher in the stationary phase. And if K is getting less, then it implies that your interaction is higher with the mobile phase. So if the interaction is very high, if the solute molecule is interacting strongly with the stationary phase, then they will take too much time to elute. On the other hand, if they have very weak interaction, if the solute vaporized components are having less interaction with the stationary phase, then they are going to elute very fast. So you have to avoid these two limiting conditions, okay, so that you can have a very good resolved peaks. Similarly, uniform coating. Coating must be uniform. By uniform coating means that if your coating is, if the thickness of the coating is too high, then what happens, besides partitioning, adsorption also starts, or adsorption also comes into play. And if adsorption comes into play, then some solute molecules are being adsorbed and some are being partitioned, then it will actually give you uneven peaks in the chromatogram. That actually leads to compromising of your separation. Similarly, selectivity is also important. We have discussed it. Now selectivity is also important. We are going to discuss this point in detail. That is how selectivity, because if your stationary phase is non-polar, for example, and your solute or the component of the volatile component are also non-polar, then they are going to interact very good. Similarly, polar are going to interact. So you have to make sure that you have to maintain the age-old concept of light dissolves light. So non-polar analyte will prefer the non-polar stationary phase. Similarly, the polar analyte will prefer the polar stationary phase. Now, what happens is, for example, let us consider siloxanes. Now, if you in terms of chemical structure, if you study the structure, then you will find the structure of siloxanes like this. Now this hydroxy group actually offers the interaction with the you can say polar compounds. So it offers high interaction with the polar compounds. So polar groups are going to interact these, and now there are chances of adsorption. But at the same time, if you replace these hydroxy group with methyl group, then what you get? You will get a stationary phase like this. Now what happens is that now you have replaced OH by methyl group. Now this stationary phase becomes almost non-polar. It becomes almost non-polar. And the moment it becomes non-polar, it is going to favor the non-polar analyte. Okay, so this actually becomes dimethyl, or you can say polydimethyl siloxane. And this comes under the name of SE30, which we are going to study. This is the trade name of it. So this is how actually you have to keep in mind about the structural aspect of the stationary phase also. So polarity is very important. Now, for example, we have in the previous slide we have discussed a non-polar stationary phase, and the examples were Se30. That is, Se30 is actually polydimethyl siloxane. And since another example is OV1. Similarly, these actually non-polar phases prefer the separation of non-polar analytes. For example, hydrocarbons. Similarly, if you have a polar, for example, if you replace in the same one, if you replace it with phenyl group, for example, C6H5, CH3, if you replace it with this, now this becomes polyphenyl methyl siloxane. Okay. Now, with the introduction of this phenyl group, you have actually facilitated its interaction with some pi-pi interaction you have facilitated. So this actually comes in between the extremely non-polar and extremely polar. So a good example of a polar, you can say polar stationary phase, is the Carbovex 20. Carbovex 20 is the trade name of polyethylene glycol. Okay, polyethylene glycol. Now you can clearly see because of the presence of OH group, now it shows high polarity. And because it shows high polarity, so it prefers to separate alcohols and esters, which are again polar compounds. So what we actually observe that if we have non-polar analytes, then they will prefer the non-polar stationary phase. Similarly, if we have polar analyte, or you can say if we have polar components to separate, then we have to use polar stationary phase. And we have given two examples, and this is the example of intermediate. We are going to study all these in details in the coming slides. Thank you very much. Thank you.